fundamental things that we learn is the ripple adder, right? And carry look ahead adder. Ripple adder and carry look ahead adder, right? We fundamentally have seen that these two adders are binary adders, right? You are given an n-bit binary number, two of them, and we know how to add two different binary numbers through either a ripple adder, okay, which consists of multiple full adders, and carry look ahead adder, on the other hand, generates the carry information up ahead so that we don't have to wait for the carry information to propagate through the full adders. So just to give you a reminder for 4 bits, okay, we've got these full adders, right? Full adder, full adder, full adder, and full adder. And we have, let's suppose that this is A3, B3, A2, B2, and we're trying to add, of course, 4-bit numbers, A3, A2, A1, A0, B3, B2, B1, B0. We're trying to add them in the binary domain where AI, BI are from the binary domain, right? They can be 0 or 1. And we're trying to figure out a circuit that does this addition operation in binary domain. And we come up with this simple idea that takes these AIs and BIs, right? And this is Cn, or sometimes we call it C0, okay? And you get C0, which is 0 in the addition formulation, right? This is set to 0 in addition, in the addition operation. And we got A0, B0, so that's exactly what we're doing here. You got this A0 and B0. When you add them together, you get a number, and that is your sum, okay? So the output of this full adder is S0, which is this sum. However, this sum can create a carry information, which needs to be propagated to the next level or next stage in your addition process. Okay? What does that mean? That means this is going to create a carry information, which we call C1. Okay? That C1 now gets added to A1 and B1, okay, to generate a sum and a carry. Okay? And if you remember, you got AI, BI, CI, right? And these are all, you have to write all the combinations here, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And you generate a sum and a carry, right? For example, if you add 0, 0, 0, you get a sum 0 and carry 0, right? If you got 0, 0, 1, you got sum 1, carry 0, right? All right?
So the C1 is the carry of A0 and B0, right?
Yes. That's the carry A0 and B0. You got C0. You add them together. This is your carry. This is your sum. Okay? This is actually this you can think of this as Cn and this to be C out. Okay? Maybe I should write C out and Cn for this particular table. But that C and C out, of course, changes as you propagate through these flippers. Take a little look at this one. This is A0, B0, C0 that generates a C1 and S0. And then similarly, you got A1, B1, C1 that generates a C2 and an S1. Again, you got A2, B2, C2 that generates C3 and S2. And you got A3, B3, C3 that generates C4 and S2. Okay? We'll actually find the same table again and again and again. All right?
C4, C0?
Yeah, C4, sometimes we call it C out. It's the same thing. Yes. That's your C8. So if you write everything down here, C1, S1, S2, S3, and this here is your C4 or sometimes C out. Okay, and question?
Yeah, if we solve the second part of the table, A0, B0, but C1, so we can say that there have to be a past in equation. Because C is 1.
This is C0, B0, A0.
Yes.
C0, B0, A0. Or
yes.
it could be C1, B1, A1. C1, A1, B1.
Yes, but if we solve A0, B0, but C1, so we
Why are you putting C1 here? A0
No,
and B0 gets split with C0.
the digits, not
The digits.
The digits, not the number of C. I mean the summation.
You mean this?
Second part of the summation. No, second line.
You mean second column?
No, the second row.
Second row.
Yeah.
Okay.
So C1 but A0 and B0. So we can say there is a past equation because never mind.
Say it, try it. So, for this particular example, are you suspicious about this result?
Because A0 and B0 but C1, so we can say.
Then why are you talking about, why are we focusing on C1 all the time? You're saying C1, C1, but this is A0, B0, C0, not
C
C1.
is 1. Okay.
C is 1, or
Yeah.
C0 is 1. C0 is 1, okay.
So we can say there have to be a past equation too, because A is 0, B is 0, but C is 1. Never mind.
No, what I'm saying is, I'm covering all possibilities. You may say that C0 cannot be 1.
Yeah.
That's the correct statement for addition operation. But we're going to be using the same table for the second stage as well, where you can have C1 as 1, right?
Okay.
So this table is not just for the first stage, it's applicable to all stages. That's why I am only drawing this table only once, okay, and apply it to first stage, and then second stage, and third stage, and then fourth stage. All right, is that clear now?
Yeah.
Okay, but you are right that C1 cannot be 1 for addition operation. When you have an addition operation, okay, the C0 is 0. Okay? But in our Monday meeting, if you remember, we also use this circuit to do subtraction, right? Remember, if you would like to subtract a binary number B from A, what we're doing, if A is greater than B, we take the 2's complement of, let's say, 2's complement of B plus A, which will give us the result, okay? A minus B. Because 2's complement of B is negative B. Okay, that's our definition. On the other hand, if A is smaller than B, we do exactly the same thing. However, what we get is 2's complement of B minus A, right? In other words, minus B minus A, which is exactly what we're looking for, right? A minus B. But since this is smaller, okay, that's why we usually express it this way. In other words, computer stores a negative number by taking its 2's complement. Okay? I mean, when you want to find out, for example, minus 3 in your computer, it's not like 3 is stored and you want to get the minus, you take the 2's complement. No way. The 2's complement of 3 is exactly what you will find in memory. Okay? Because the negative numbers are stored as 2's complements. Okay, go ahead.
Should be minus A minus B.
Oops. Correct. This should be A minus B, right? No, this is B minus, 2's complement of B minus A, because this is positive number, and this is negative A minus B. Correct. Thank you.
How when A and B is 0, how S can be 1?
You mean A and B are 0? What?
When A and B are 0,
Yes?
why S can be 1?
S
Yes.
was because C can be 1. The carry information could be 1. Right? Think about the second stage. Second stage. You got 0, 0, and this is 1. What do you expect S1 to be? This should be 1, right? Right? Okay. Any more questions? All right, so we also have seen that remembering this formulation for subtraction, we realize that we can use the same circuit again to do the subtraction, okay? What does that mean? That means we can actually take the complement, one's complement of b, right? And add 1 to that so that you got 2's complement, and that's exactly what you're looking for, and then add it to a to get a minus b, okay? Let's focus on this, the rest is just the same, so that's why I'm going to be focusing on this one. So instead of drawing the circuit like that, maybe I can actually put, as I said in my Monday's meeting, a mux maybe, right? A mux. That's exactly how you'll design your CPU, by the way, okay? When you want to do a resource resharing, like you want to use the same circuit for different functionality, then you have to add simple circuit elements like muxes, decoder, encoder, those stuff, so that you can have only a minor increase in your complexity, hardware complexity, but you're able to do multiple different things. Okay, that's exactly the idea behind hardware design. Here, for example, you add a mux, for example. You use 4 different muxes. Okay, and of course you need a select input. Because if you select 0, you will get B3 as is. Similarly here, you have B2 as is, B1 as is, B0 as is. However, if you select, and this is going to be, of course, the same select input for all of them, right? This is your select. And if you have selected 0, then you will have B3, B2, B1, B0. Okay? But if you would like to select the negated version of B or the inverted version of B, then you may want to actually put a NOT gate, right, and then connect it to B. Okay, maybe I can use more space to show you that. All right, so let's just erase and secure more space. Okay, see if that goes anywhere. All right, so we have B0, okay, coming in here, and a NOT gate version, or negated or inverted version, goes to the other gate. Okay, so this is B1, for example. I have a negated version that going to the other select, the other input of the mux. And we have B1, for example, and then you have the NOT version or negated version going to the other input, and we have this one, okay? All right, now, if I select 1, right, if this is equal 1, then I'm going to choose B0 not, B1 not, B1, I'm sorry, this is B2. B2 not and B3 not at the input of the flippers. And that's exactly the 1's complement of B. All right? Now, even further, I can just connect that to Cin, okay? All right, so that means if select is 0, there's no problem because it's going to select B0, B1, B2, B3 and set Cin to 0, and that's exactly what I expect for an addition operation, binary addition. But if I set select to 1, that would generate, first of all, it will select B0 prime, B1 prime, B2 prime, B3 prime, that's 1's complement, and set Cin to B1, and that one gets added to this B1's complement, makes it 2's complement, so that you have A, okay, that goes through without any logic, you see, plus to B's complement, 2's complement of B, sorry, 2's complement of B, so therefore you implement A minus B. Okay? So this is of course one option. I think it's more straightforward option, but it turns out that there's an easier way. Instead of using a mux, you can actually replace each mux with an XOR operation. Okay? We actually shown that. If you just replace with an XOR, sorry, my drawing is kind of bad, but this is your XOR. Or maybe I can draw it here for you. This is my XOR. Okay, turn it down 90 degrees clockwise. You get this, and just add this. This is first input, this is second input, this is your output. Okay, to the XOR gate. And we have shown that this has the exact same functionality of a mux operator. And this is, of course, easier than implementing a mux operator. So usually we prefer putting an XOR here, 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 and here to implement a subtractor. Adder, binary adder, and a subtractor. Okay, you see that the idea here is to maximize the resource utilization. We only have 4 full adders, you see? And we are able to implement addition and subtraction at the same time. Okay, the only additional hardware is 4 different XOR gates. Okay? Any question here? The only thing that I haven't covered was the overflow and underflow control mechanism, which we actually said we're just connecting the C3 and C4 through an XOR gate. Okay? That would give us the overflow, underflow, or underflow. If the result of this is 1, then there is an overflow or an underflow. And I haven't talked about why, so I'll give you a simple explanation rather than a theoretical one. So I'd like to go through that just real quick because we've got a bunch of stuff to cover today. All right, let me just give you an example. All right. Well, first of all, if you're dealing with unsigned numbers meaning that both of these numbers, A and B, are positive numbers. Okay, signed number, positive number. There's no negativity. So therefore, when you add 2 unsigned numbers, then you cannot have underflow. Right? You only can have an overflow problem because there are 2 possible positive numbers added together creates a bigger number that you cannot even represent. Since signed numbers has positivity in it, so I'm going to focus on signed numbers case because it also has the unsigned case in it. So therefore you will realize that how this kind of simple logic creates a control mechanism for overflow and underflow. So let me use 4 bits, okay, for creating a signed number system. Okay, since I have got 4 bits, I have to have 16 different rows. So it's going to take a little while to generate all these numbers. So let me just show you how. And this is going to have 4 rows in it. And this is going to also have 4 rows in it. This is your 8, 4, 2, okay, I hope that works, but probably not. Anyway, since this is a signed number system and you got 4 different bits, that means 16 different possibilities. You have to map those possibilities to both non-negative numbers and positive numbers. Okay? So what does that mean? That means you can only store the following numbers. You can have 7, 6, 5, 4, 3, 2, 1, and 0, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, and minus 8. Okay? These are all the possibilities. And what are their binary equivalents? Okay, representation. So we know that 0, 0 has to be 0, 0, 0, 0, right? And we know that what 1 is 0, 0, 0, 1, right? How about we take that 1 and take the 2's complement? In other words, take the 1's complement of that number, it's going to be 1, 1, 1, 0, and add 1 to that, you got 1, 1, 1, 1, 1, right? So therefore, you got 1, 1, 1, 1 here for minus 1. Okay? Now I'm figuring out from the positive numbers, using our rule for 2's complement, we can figure out the negative numbers. Okay? So 2, for example, is 0, 0, 1, 0, right? What is the 2's complement of 2?
1, 1, 0, 1.
1, 1?
0, 1.
1, 1, 0, 1. Okay, let me check. Is that correct?
We have to add 1.
1 to that, because it's 1's complement, right? So your 2's complement is going to be 1, 1, 1, 0. Okay? How about 3? 0, 0, 1, 1. it's going to be 1, 1, 0, 1, right. And similarly, you got 1, 1, 0, 0. You got 1, 0, 1, 1. You got 1, 0, 1, 0. You got 1, 0, 0, 1. And finally, you got 1, 0, 0, 0. How about the rest? 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, and 0, 1, 1, 1. All right, you realize that we actually covered all 16 possibilities in here. All right? All 16 possibilities. And unlike the unsigned case, where we have this is 0, this is 1, 2, 3, 4, 5, 6, 7, and 8 is which one? This one, right? In the unsigned case. However, in signed case, this becomes minus 8 instead. Okay, for example, this corresponds to a 9 in unsigned case. In the signed case, this corresponds to minus 7. It's all about representation. How do you define numbers? For example, here I use 4 bits to define both positive numbers and negative numbers. Of course, that caused me not to go beyond 7 in the positive direction and not to go below minus 8 in the negative direction. Okay, because I've got only 16 possibilities. All right, now coming back to our original question, overflow and underflow control mechanism. Well, if you look at the positive numbers in this signed case always have, one of the things we realize, always have 0 in the most significant bit position. Right? In the MSB, you always have a 0 in the most significant position. For the negative numbers, actually 0 is not a positive number, right? But it has a 0, okay, as a convention. How about negative numbers? In the negative direction, you see negative numbers has a 1 in the most significant, okay, MSB bit location, right? They always have a 1 in the most significant bit position. So therefore, we can identify a positive number and a negative number by just looking at the MSB. Okay? That's a good sign because that's why we actually call them signed and unsigned numbers. In the signed numbers, you look at that sign to realize that it's a positive number or is a negative number or is a negative number. Okay? That's why the name came from, signed and unsigned. Because in the unsigned case, there is no such a sign of a negativity or positivity. In the signed numbers, there is a sign that gives you ability identify is that if the number is a positive number or a negative number. All right, that's the first thing we realized. Second thing we realized that if you add 2 positive numbers that are going to generate an overflow, okay, you have to have a big number, right? There is this 3 plus 2 will not generate an overflow problem because 3 plus 2 is 5 and 5 is representable in your table, okay? So 2 and 3 will not going to generate any problem. Or maybe 3 plus 3, for example. It will generate 6, but 6 is already representable. Okay, so what you have to focus most of the time is these top numbers like 4, 5, 6, and 7. Because if you got 3 plus 7, 4 plus 3 is 7, that's representable, but 4 plus 4 is not representable. It's 8, and it's 8 is not in your table. Okay, so it starts from 4 and above, that might be a problem. Okay, and if you look them carefully, you see, all right, these 2, maybe we should focus on these numbers. These numbers are B2 and A2, right? B2 and A2. A2 and B2, and they're both 1s. Okay? So these are actually giving you 1 and 1 here. Okay? Irrespective of what C2 is, this is going to create a C31 automatically because there are 2 1s already. All right, so C2, if it is 0 or 1, doesn't matter. It's going to create C31. Okay? Okay, that is in our hand now. Second thing we realize, this is A3B3, right? A3B3 are both zeros. So these are going to be 0, 0. Okay? Therefore, irrespective of what C3 is, C4 is going to be 0 because it's 0, 0. So therefore, C4 0, C3 1 can generate an overflow problem. Okay? C3 is 1, C4 is 0, could be an overflow problem. Okay? And actually it will be because If you got 4, 5, 6, 7, take any two and add them together. It's going to create an overflow problem. Okay? Take any two and add them together. So therefore, if C3 is 1 and C4 is 0, that is an overflow problem. Similarly, in the negative direction, if we got two negative numbers added together, and those negative numbers are large negative numbers, let's say. In other words, if you take 5, minus 5, minus 6, minus 7, and minus 8, if you add them, take any two and add them together, what you will get, for example, take minus 5 and plus minus 6. What do you get? You get minus 11, right? But that is not representable in your table because your table can only store minus 8 as the most negative number. Okay? Or maybe you can take, for example, minus 4 and minus 5. That's going to create minus 9. That's not representable. But minus 4, I didn't take minus 4. Why? Because minus 4 gives you minus 8, but minus 8 is representable. That's why I took these last four. And if I again look at carefully, I realize that the A2B2, here A2B2, they're both 0, 0, right? They're both 0, 0. Therefore, this is 0, this is 0. Irrespective of what C2 is, it's going to create C3 0, okay? Because this is 0, this is 0. However, on the other hand, if you look at the most significant bits, they're both 1. Therefore, A3 and B3 is going to be 1, 1. Irrespective of what C3 is, C4 is going to be 1. And that will create your underflow problem. Right? Because we proved it. You can minus 5, minus 6, minus 7, take any two, it will create an underflow problem. And the property of these four numbers is that their A3, B3 are both 1, and their A2, B2 are both 0. Okay? That's why we have got another rule, which is C3 equals 0, and C4 equals 1. That creates underflow problem. Okay? Therefore, if you combine them, this is actually the simple logic of finding C3 and C4 different. Right? We have to check whether C3 and C4 are different. If they're equal, there is no underflow, there is no overflow. But if they're different, in this case, for example, if C3 is 1 and C4 is 0, it's an overflow problem. And if C3 is 0, C4 is 1, it's an underflow problem. And the property that these two conditions share is that they are different. C3 is, when C3 is 1, C4 gotta be 0. And if C3 is 0, then C4 gotta be 1. Therefore, there is a simple gate that checks that, which is XOR. Because in the XOR case, if the inputs are the same, the output is 0. Think about it. 0, 0 gives you 0. If it's 1, 1, gives you 0. Right? That's the XOR capability. However, if the inputs are different, then XOR will give you a 1. If it is 0, 1, it gives you 1. If it is 1, 0, it gives you 1. So therefore, that's why we put an XOR here, okay, to catch that. Okay? If you're able to catch either one of these, then you can catch overflow and underflow control mechanism. Okay? That's why it turns out that we have a simple gate, okay, that catches this simple problem. Although it's simple, we can actually come across such a problem in any digital circuit. So it is actually a lifesaver property of the circuit. Okay? I hope this is clear. As I said before, we've gone through an example, but you can check it with any bits, not just 4. This is n equals 4 case, right? Not just 4, but you can check with any, like general n. You will have this property because we're identifying, this is property, sorry, not problem. But the property that we're identifying is general property, not just applicable to n equal 4 case. If n equals n, like general n, then you have got 2 to the n rows, right? And n of the numbers from bottom and n numbers, Let me just not generalize that way because that might be wrong. But some numbers on the top and some numbers on the bottom will actually have this property, okay? And we will use the same logic, in fact, to get to the overflow and underflow control, okay? Anyway, question?
So when we apply this in hardware, for example, in real life, when we get a 0 or 1, we will say that, for example, when we get 0, we will say that, oh, there's a problem, there's an overflow.
No, when you get zero, that means your calculation is right. Because there is no overflow or underflow, right? If you have got a 1, okay, then you will realize that, I mean, this circuit will generate something, right? It will generate S0 some number, S1 some number, but this will tell you this is not reliable. This is not reliable. I mean, you did something, but you did it wrong. I mean, let me give you an example. For instance, I want to calculate the following. -7 minus 5, let's say, okay? This is going to -7 plus 5, it's going to create what? -2, right? This is representable. -7 is representable. -5 is representable. -2 is representable. Okay? So this would actually push out a 0 because this is a valid calculation. Okay? I mean, you can go through and apply the logic here and you will realize that -2, this would result. This would be your result. Okay, without any problems. How about the following question? -7 I'm sorry, not -7, but 7, let's say 7 minus -5. 7 minus -5. 7 is representable, right? There's 7 here. -5 is here. And if you take the difference, what you get? You got 12. But 12 is not representable. So this circuit has to tell you there's a problem. Okay? And let's just carry out the calculation. Okay? We know how the circuit works, right? So let's take 7. It's 0, 1, 1, 1. Okay? Let me erase the bottom. Okay? Let me write it down. Again, 7 minus -5, right? So this is my 7. And what is -5? Is 1, 0, 1, 1, right? 1, 0, 1, 1. And this is a negative, right? So instead of doing this, what we do in the hardware is this is 0, 1, 1, 1, but we take the 2's complement of this because there's a negative number, right? If you take the 2's complement of 1, 0, 1, 1, what do you get?
0, 1, 0, 1.
0, 1, 0, 1, right? Okay. This can be done with our hardware because hardware knows how to calculate these two. Okay? I mean, how to add these two. So what do you get? 0. We got to carry. I'm actually implementing it. You see, C1 becomes 1 now. Okay. This is a 1, so we got 0. Another carry 0. I'm sorry, not 0. 1, 1, and a 1. You see, and there is no 0. I mean, C4 is 0, right? Okay, so let's look at, so we actually care about this 4 bits, right? We don't have any space to store that bit. This is just 0, right? So this has got to be 4 bits, and we got 1, 1, 0. Let's just look up our table, because that's going to tell us the decimal equivalent. What is 1, 1, 0, 0? -4, right? This is -4. So the circuit says that your answer is -4. However, my actual result is 12. You see the error now? I mean, you figure out that it's specific output, but that output is not reliable because your C4 is 0, C3 is 1, and you know from an XOR operation that this is going to create a 1, and that would tell you, oh, the result you found as a -4 is not reliable. Okay? This is a wrong calculation. Sometimes your calculators sometimes tell you that, right? You get an answer, but the calculator says there's an overflow or an underflow, okay, indicating that there is something wrong with the output. Okay, so that's why this type of catch mechanisms, this control mechanism, is vital in the development of a digital system. Any questions?
You know that truth table for XOR gate?
The XOR gate truth table, okay. Let's draw that, just for reference. All right. XOR gate actually finds out if there is anything different in the inputs. Okay, that's what usually we use XOR for. But let me give you the truth table, A, B, and this is A XOR B. This is the way we represent XOR, by the way. 0, 0, 0, 1, 1, 0, 1, 1. 0, 0 XOR, you got 0. This is just like a sum in your addition, arithmetic addition. The sum generates 1 here, and 0 here, right? So 1 plus 1 generates a sum 0 and carry 1, right? So this is exactly your sum. Remember your sum in a half adder? Sum was A XOR B, right? And carry was A and B, right? Remember that? So it's actually XOR is defined to be the sum of the half adder. And in fact, in the full adder, if you remember, there were 3 inputs. The sum turns out to be A XOR B XOR C. Remember that? So again, the sum is an XOR. Right.
When we look at the 5-bit perspective with this subtraction, it's, I think, correct. Can we say that?
Well, you have to have a table then, 5-bit table.
Yes, but I want to focus different.
Okay.
If this XOR gate return 1, can we say that, or we can do like this circuit? If this is 1, you can calculate this 5-bit perspective.
Yes, you can say that.
Am I correct?
Yes, you can say that. In fact, in that case, if you want to translate to 5 bits, then you have to put an extra full adder here,
Yes.
and your XOR now will connect this one and the following C out, not these two now, right?
Yes.
That we were connecting the XOR, the output of the last full adder and the one before that. Okay, that's always the case. For an n-bit, for example, adder, you have to figure out the output of the last full adder and the one before that, okay? Or the one preceding that full adder. Okay. Okay, so this was that, and I want to also talk about today the decimal adder, right? The decimal adder. So let me briefly talk about the decimal adder because, calculators, us as humans, right, are not good at binary numbers. That's not how we're taught in high school or in any educational institutes. What we do instead is the decimal addition operation, right? What does that mean? In calculators, we have, for example, 21, 1, 7. We add them, right? Remember your primary school days? What you do is you get 1 plus 7, you write 8, and you take 2 and 1, and you write 3. And that's exactly how the calculators do the calculation. However, underneath in the hardware, the things gets translated into binary domain, and then we use those type of binary adders, and we finally translate the output to these decimal numbers. Okay? Those decimal numbers has to be represented somehow, and in the calculators we use binary coded decimal formulation or representation of these numbers. So in fact, let's suppose we've got 4 bits, let's say, okay? I'm going to continue with my 4-bit example. So let's suppose that there are 2 4-bit numbers, okay? Suppose, for example, we have, for instance, if you'd like to translate this 2-1 into binary coded decimal, remember, 2 was represented by 0010, and 1 is represented by 0001. So we use 8 bits to represent 2-1, in other words, 21. Okay? If we were to use only binary domain, then 21 would of course take less number of bits, right? Can you tell, top of your head, how many bits you would need to represent 21 in an unsigned number system? 6, right? Because 2 to the 5, 2 to the 4 actually. 2 to the 4 gives you 16. So 2 to the 5 is just 5 bits is enough for unsigned number system. So just 5 bits is enough. But we use 8 bits to represent 21 in binary coded decimal. All right, B, C, D. This is just another mapping strategy. And calculators use B, C, D to represent numbers. Like digits, not numbers, but digits. We're not trying to represent the number. We're trying to represent the digits itself. Okay, so 2 is this, 1 is that, and 1 is this, 0, 0, 0, 1, and 7 is 0, 1, 1, 1. Okay, and we add them. In fact, we add in digit by digit in the binary coded decimal domain. So, for example, if you take 7 and 1, you add them together. What do you get? You get 8. And in fact, it turns out that if you just apply this 4-bit binary adder, let's apply it. 1 plus 1 is 0. We got to carry 1. We got 1 here. Again, we got 0. Again, with 0 and 1. Is that 8 in binary domain? Yes, it is 8. Okay? And similarly, 2 and 1, add them together. You got 1, 1, 0, 0. Is this 3? Yes. And is this 8? Yes. And did we figure out the answer? Yes. This worked very well. How about the following? 25 and 36, for example. Okay? Would the same logic work? Well, we have 2, 0, 0, 1, 0. 3 is 0, 0, 1, 1. This would definitely work. 1, 0, 1, 0. What is that? 5, right? In my binary domain. So this worked. How about 5, 6? This is 0, 1, 0, and this is 0, 1, 1, 0. If you add them together, you got 1, 1, 0, and 1. What is that number? 11. 11. But 11 is not a digit. How the calculator will interpret this result? Okay? Here is the problem. That's why we need to do some kind of transformation. What does that mean? When we have numbers like 5 and 6, in other words, any two numbers, that generates a digit greater than 9. Because when we have a greater than 9 digit problem, it is the problem. That's the essence of the problem. We have to focus on the cases where we have the sum greater than 9 or greater than or equal to 10. Okay? So therefore, I'm going to actually write those cases only. The rest is just the same. The rest is just going to give you what you want. Okay? But when you have these cases, then you have to do something. What are you going to do, by the way? What's the result of 5 plus 6? Let's just forget about this example, but let's just focus on 5 plus 6. What is the result of this in the calculator? You got 5, 6, 11, right? There's going to be a 1 and 1. What does that mean? That means 0, 0, 0, 0, 1 and 0, 0, 0, 1. So therefore, this is 1, this is 1. So what is happening here? If you have, the addition operation, it's 11 in the binary domain, but in the binary coded decimal, you figured it out as 1 and 1. In this case, you got this number rather than 11. Okay? What's happening here is that if you have, so instead of writing like this, for example, 1, 1, okay, which is 11, which is not representable, what we're writing is, we're basically separating this, right? We write a 1 here, and then that 1, this 1, is the carry that we carry to the next, in the next level, which we propagate that to the next level. So instead of having 2 plus 2, 3, we got an extra 1 coming from the previous stage, making this total sum 6, right, rather than 5. So the outcome of this is going to be 0, 0, 0, 1, and we have got extra number 0, 0, 1, right, coming from the previous stage. That's going to make it 6. We're fine in this case because 6 is representable. Okay? So that's why 0, 1, 1, 0 is the final answer of this particular example. Because this is going to be 1, this is going to be 6, right? Which is 61, and that's exactly what we're looking for in the calculator. Okay? So let's focus on these cases, like two numbers given us greater than 9. Let me just write them down because they can be 10, 11, 12, 13, 14, 15, 16, not 16, 15, right? That's the exact, This is the number that we can create as the maximum of the two, or maybe not, right? Because we got 5, for example, we can have 9, 9, 18, right? 18, and maybe we can have an extra one coming from the previous stage, makes it 19. So 19 is the biggest number we can get in the decimal domain. So we have to actually carry on. 16, 17, 18, 19. All right? So we have to think about all these possibilities because these are the cases we have to deal with the problem. Okay? Is the 9 problem? No, because 9 is representable. Okay? All right. So I'm going to name those binary digits. Because now we have got 19, I need 5 bits. I have to introduce the 5th bit because 19 cannot be represented using 4 bits. So I'm going to actually write down the following. K is my new bit, by the way. Okay? And I've got the other bits as named as 8, 4, E2, or E1. You could actually create E0, E1, E2, E2 as well. This is just my notation. Okay, because it's 8421 code. That's why I use that notation. All right, so what is 10 in this notation? Binary representation of 10 is the following. You got 1, 0, 1, 0, right? That's your 10. And what's K? It's 0. K is my extra bit, by the way. Okay, let's continue. What's 11? 1, 0, 1, 1. This is 0. What's 12? 1, 0. I'm sorry, not 0. 1, 1, 0, 0, right? This is 0 again. 13 is 1, 1, 0, 1. This is 0. What's 14? 0, 1, 1, 1, 0. What's 15? 0, 1, 1, 1, 1. Okay? Everybody happy? How about 16? You got has to now be this extra bit now has to be 1. Because otherwise you cannot present 16. These are all zeros. But fortunately we got only 4 of them. 4, 0, 0, 0, 1, 1, 0, 0, 1, 0, and 1, 0, 0, 1, 1. Remember, this is the 5-bit representation of 19. Okay? Once you get 4-bit, 4 bits and 4 bits, remember, this circuit here will generate 5 bits, right? First bit, second bit, third bit, fourth bit, 5 bits. Okay? So you can use that circuit actually to do this calculation and get this result. 5-bit representation of 19 at maximum. Because that's the maximum number you can get. Okay? By adding 2 digits. Alright, now we have to deal with it. How are we going to deal with it? We're going to have to do the translation. Right? Translation. What is translation? Translation is this. We have to translate it to this. Okay? So let's just write the BCD sum also. I told you before, it's going to get more challenging and challenging every day. All right. If you lose it in the beginning, you lose it all. There will be no more motivation for you to catch up with the class. Okay? You have to find your own motivation. Okay, so, but I'll do my best, of course, to catch you up. If you've got any problems, questions, please interrupt me anytime so I can, go back and remind you a few fundamentals and then come back to today. All right, so this is your 10. This is your 10, and I want to represent this 10 by the BCD sum. What is BCD sum? BCD sum, I'm going to use different, letters. What is BCD sum? BCD sum contains, remember, there's going to be 2 digits, but instead of, writing these 2, 3, I'm going to focus on only 1 digit, digit 1, digit 2. I'm going to focus on 2-digit addition only, all right? So that means you can have, let's say this is C, this is my extra bit, and the rest of them are S8, S4, S2, S1. These are, again, notation. So what does that mean? Well, 10 cannot be represented that way in the BCD domain. This is BCD, right? In the BCD domain, 10 is the following. You got 0 for the last 4 bits. And the first 4 bits, I actually missed the 3 of them because 3 of them always will be 0. That's why I only use 1 bit here. But that would be 1. This is my 10 in the BCD domain. Because this corresponds to 0, this corresponds to 1, right? This is my 1 here, and this is my 0 here, 4 bits. I use 4 bits to represent the digit. You would say, oh, you got only 1 bit to represent this digit? No. There are 3 zeros, but I didn't really want to put those zeros here to complicate everything. I only use, because I would only need 1 bit actually. Okay? Because you see, there's only 1 here. There's no 2, because 19 is the maximum. That's why I don't have 2. If I had 2, then I have to use 2 bits here. Okay? Alright, so this actually you can guess would be always 1. How about the rest of the 4 bits? Well, you can see 11, this is 1. So I'm going to have 0, 0, 0, 1. This is 2, 0, 0, 1, 0. This is 3, 0, 0, 1, 1. This is 4, 0, 1, 0, 0. 5, 0, 1, 0, 1. 0, 1, 1, 0, 0, 1, 1, 1. This is 7. How about 8, 1, 0, 0, 0, and 1, 0, 0, 1. Okay? You see now, you got 5 columns on the left-hand side and 5 columns on the right-hand side. Okay? And they're not identical. You can see that they're not identical. Okay? And what I care is that for these particular cases, not the rest of them, right? There are other 10 cases that generate 0 to 9 digit. They're not problem. But these are problem. That's why I'm only focused on those problematic cases. And you got 5 inputs and 5 outputs. It's just like the functions we implemented, in our previous classes, where we have Carnot maps and we do these modifications, etc. All these simplifications, right? You can actually apply it here because now you got the truth table. Okay? Since you have the truth table, you can actually find out the Boolean expression that corresponds to, C, for example. Okay? For example, C turns out to be C. You may say, oh, C is always 1. What are you talking about? C must be 1. No. Why? Because we got the other 10 cases here that generate C0, right? That's why. So C is not always 1. C is sometimes 0, sometimes is 1. So what's the condition for that? It's pretty simple, it turns out. C equals K plus, actually or, E8 and E4 plus E2. Okay, that's your C. All right? You can actually figure out this using, again, using your previous background on Boolean algebra or Carnot maps, etc., etc. Okay? It's not a big deal to find out. I mean, you can actually, if you write the full table, you can actually verify that. It's quite easy to verify. Okay, so why did I find C? Because the reason is, if you got 10, for instance, you got a 0. So this is kind of easy to represent already, right? These are just our, numbers. We know from 0 to 9, right? 0 to 9. Right? 0 to 9. And we know how to represent them already because the previous 10 case, actually those cases. Right? Those cases. So in your truth table, actually in your complete table, you got 20 rows. 10 of them are not represented here, but the rest of the 10 is here. Okay? So let's just focus on the logic diagram that uses this 4-bit logic, 4-bit adder. Okay? So let me just first put this 4-bit adder here. Adder. You can implement this 4-bit adder using a ripple adder or carry lookup adder. Doesn't matter. What you get is A0, B0. You got A1, B1. You got A2, B2. And you got A3, B3. These are 4 bits of the 2 numbers you would like to add. Okay? And there's a Cin, of course. And these are the outputs. What are the outputs? E1 is your least significant, E1. E2, I'm sorry, E2, yes, E2. This is E4, this is E8. These are the sum values here, you see. Alright? E1, E2, E4, E8. Your sum values. Alright, and finally we got an output. That output is your? This is K, right? K. Your K. Because K is your output, right? The C out. You see? Sometimes you get ones because it's an overflow, right? Of course, your overflow indicator will tell you there's a problem, right? But you may choose not to care about it, right? Because it's going to be used for another purpose for this circuit. Okay? Anyway, so you got these E1, E2, E4, E4, E8, and K. And I would like to, of course, implement C because that's my first digit, right? So it's pretty easy to implement because you got E2 and E4 OR together, right? And this is OR, E4 OR together. And that OR is ended with E8, right? And we have this OR with K. So this K is OR together to find out your C. This is your first digit, right? First digit is C. How about the rest of them? Well, rest of them turns out to be pretty easy because remember, the binary equivalent of, take two digits, add them together in the binary domain, okay? For example, we got 5 and 6, right? If you add them together in the binary domain, what do we get? We get 5, 11, right? And what is 11 in the binary domain? 1, 0, 1, 1, right? Okay. When we add 6 to that, 0, 1, 1, 0, what do you get? 1, 0, 0, 0, 1, right? And that's exactly what I'm looking for, right? Because it's 11. This one is right here, and this one is 1 here. So in order to translate from the binary result to a BCD domain, you just have to add 6. Remember the homework question? Yes. That's exactly what you were working for in the homework question. There's a 6 difference between the binary addition output of this circuit, okay, and the BCD output. Okay? If you are, of course, concerned with only 2-digit addition. Okay? I'm not talking about this one. I'm talking about 2 digits. Because I focus on 2-digit and I apply that circuit here and then here and then here and then here. You will see that. This would be just like the binary version where you will have a C in, C out, and 2 numbers. 2 digits actually. Instead of 2 binary numbers, 2 digits now. All right, now, so therefore I have to take this E1, E2, E4, and E8, and I have to add 6 to that. But I can do that only using another 4-bit adder. Okay, because these are binary numbers. So I have to put another adder here, 4-bit adder. Okay? Okay, these are good, these are just bits, but I have to add a 6. But what is 6? 0, 1, 1, 0, right? No problem? Okay. So I have to put a 0, right? Here, a 0 here, right? So that you got 0, 0. These are these 2 zeros. And I have to put a 1 here and 1 here, right? But instead of doing that, since I have C always 1, for this particular case, C is always 1, right? When you add 6, because you don't add 6 in the general case. For example, you have 2, 3. Do you add 6? No, because 2, 3 does not generate the problem. We're always focusing on the problems that we're generating when we have the sum greater than 9. In those cases, C is always 1. You see? Therefore, instead of generating a 1 and pushing it, I can actually get the C out and then push it here and here. Because when there is no problem, C would be 0, so you add 0, 0, 0, 0 to that adder, the output would not be affected by that. But if C is 1, that would actually make it this 1 and this 1. 0, 1, 1, 0 actually is a 6. So that would create the correct result. Okay? So therefore, I connect it to C. You cannot connect it to 1 here because it's going to be fixed. And it will always add 6 to your result, and that's not right. Because if your digits are such as 2 and 3, there's no problem with the summation because it generates 5, and 5 is representable. So therefore, this has to be 0, this has to be 0. But if you put it, fix it to 1, it would generate that result plus 6, which would be wrong. Okay? That's why I connected to C. Because C is always 1 when you have a problem with your translation.
Can you use sign numbers?
With sign numbers, well, in your decimal adder, sign numbers are not affecting your digits, right? If you got a 9 minus number here, that minus is not just for this digit, it's for the number. I'm adding here digits only. Okay, so if you got sign, you mean, I think you mean, you meant to say minus decimal numbers, I think, because we're dealing with decimal numbers. So if you got 21 and minus 34, you know, if you add them together, it's just like additional 21, 34. So you add the minus sign in front, okay?
When we are representing them in white digits, express them like this.
These not, I mean, sign number example here is for binary numbers. I'm talking about decimal numbers. Okay? So decimal numbers, if we come up with the decimal equivalent,